Hi, now let's talk about relationship between oxidation potential and reduction potential, right? Since if we talk about this half cell has zinc dipped in zinc sulfate, right? And zinc is getting oxidized because its oxidation potential is high, right? So what about its reduction potential? We say that oxidation is reverse of reduction, right? So if we say oxidation potential, that is ability to oxidize of a certain metal, right, is higher, right? So what about reduction potential, that is ability to get reduced? Since oxidation we say is reverse of reduction, right? Oxidation is giving electrons, reduction is gaining electrons. So if we talk about reduction potential of zinc, reduction, which is exactly opposite of oxidation, so reduction potential of zinc would be same as oxidation potential but opposite in sign. What we mean by that is, we know that oxidation potential of zinc is equal to it's 0.76 volt. Oxidation potential of zinc is plus 0.76 volt, so its reduction potential would be equal to minus 0.76 volt, right? So oxidation potential and reduction potential are equal in magnitude but opposite in sign. What this means is, like, since we know that oxidation potential of zinc is plus 0.76, which is a quite high value, so that is why it gets oxidized. And if we talk about its reduction potential, that is if it can gain electrons or not, its value is minus, the same but in minus, which is a very less number. So its ability to get reduced is very low, right? And we have studied here that when the concentration of ions will increase, this reduction potential will start increasing. So this in a way depends on the concentration of ions. If we talk about here, if we talk about this cell, right? So this is, just remember this, that oxidation potential is equal in magnitude but opposite in sign, right? It's equal in magnitude but opposite in sign. So in numericals, if you get that oxidation potential of this metal is this much, what is its reduction potential? Or suppose you need to find out what is its reduction potential if one is given. If one is given, if you want to calculate the other, just reverse its sign, right? So this is important relationship between oxidation and reduction, because we would be doing this a lot in numericals. Now let's talk about standard EMF. I'm sorry, we have gone through about electrode potential. Now we have something called as standard electrode potential. Standard means electrode potential calculated at standard conditions. Standard, if we apply standard conditions to this half cell of zinc where oxidation is occurring, and we know that zinc electrode has oxidation potential, right, because it has high tendency to oxidize, right? So it has a high oxidation potential. So if we calculate the oxidation potential of zinc under standard conditions, by standard conditions we mean that the concentration of this solution in which zinc rod is dipped is 1 molar and temperature is 25 degrees Celsius, that is 298 Kelvin. Then the electrode potential that we get at 25 degrees Celsius and 1 molar solution of this zinc sulfate solution that at these conditions the electrode potential that we get is standard electrode potential. So standard electrode potential is standard conditions, 25 degrees Celsius, 1 molar solution. By solution we mean this, because whenever we calculate electrode potential, this electrode is in contact with its ions, is in contact with a solution, right? Because ions is in solution, right? So electrode is in contact with its ions in solution. So this concentration would be 1 molar and temperature would be 25 degrees Celsius. And at that, under these conditions, the electrode potential is standard electrode potential, right? So now we are almost done with electrode potential. Now let's just quickly see what is EMF, right? Electromotive force of this cell, right? EMF, electromotive force, exists, right, when we have a potential difference. EMF is nothing but a potential difference. So where do we see potential difference in this cell? We know that potential difference, like we studied here, in case of these electrical double layers, in case of these electrode potentials, we have these separation of charges, due to which we have electrode potential, right? So now let's see where we have the separation of charges in this entire cell, because EMF is of entire cell. If you look at these rods, cathode is positive, anode is negative, right? So we have these rods have opposite signs, right? Opposite charges, better. These rods have opposite charges, due to which there is potential difference, right? We have potential difference between these two, and it is due to this potential difference that current will flow in this cell, right? Since we know, if we go back to our first lecture of the working of this Daniell cell or this electrochemical cell, we saw that current flows from positive rod to negative rod. That is, current was flowing from cathode to anode, right, is in this direction. Since current was flowing in this cell, that means there exists a potential difference, right? And what is the cause of this potential difference? How does this potential difference exist? It's again the same explanation. We have reduction occurring in this half cell, reduction half cell, due to which this rod has become deficient of electrons. Deficiency of electrons means this rod will acquire a positive charge. Similarly, if we look at this oxidation half cell, due to oxidation occurring in this half cell, this rod will acquire a negative charge, right? So negative charge is due to oxidation, positive charge is due to reduction, right? Due to this oxidation and reduction reactions, these electrodes will acquire opposite charges, positive charge and negative charge. And now since we have opposite charges, due to these opposite charges, potential difference will exist. And we know that the rod that has positive charge is at higher potential, and the rod which has a negative charge is at lower potential, right? So current will flow from higher potential to lower potential in this direction, right, from cathode to anode. That is why current, when we done in the first lecture, current was flowing from cathode to anode, because cathode was at higher potential due to reduction, right? It has acquired positive charge, and anode is at lower potential due to oxidation reaction, right? So due to potential difference, I again repeat, cathode is at higher potential, anode is at lower potential, because this is positive, so this is at higher potential, this is negative, this is at lower potential. And we know that current flows from higher potential to lower potential, right, in this direction. So due to this potential difference that has developed due to oxidation reaction and reduction reaction, we have potential difference, and due to the potential difference, current will start flowing in this cell, right? So this is clear. So in short, we say that EMF, the potential difference, is nothing but EMF. EMF is the potential difference, right, that exist between these. And EMF is the maximum potential difference that exists between these rods, between the cathode and anode, when no cell is passing, when no current is passing in this cell. So when current will start passing in the cell, the potential difference will decrease. So EMF, we say, is always higher, is always maximum potential difference, right, because no current is flowing at that point. And since we said that this potential difference has developed due to oxidation and reduction reaction, which we call together, oxidation and reduction reaction is known as redox reaction. So we say due to redox reaction, potential difference has developed, due to which current is flowing in this reaction, in this cell, right. So if we want to calculate mathematically the EMF of this cell, and we know that EMF of this cell is due to oxidation and reduction occurring in these two half cells, that is due to the reduction reaction, due to the redox reaction, and redox reaction is nothing but oxidation and reduction that is taking place simultaneously. So if we want to calculate the EMF of the cell, EMF of the cell would be mathematically sum of oxidation potential of anode and reduction potential of cathode, right, mathematically. E would be oxidation potential of anode plus reduction potential of cathode, right. This is EMF. So oxidation potential, and we have just done that. What is the relation between oxidation and reduction potential? Oxidation potential would be equal but opposite in sign to reduction potential, right. And we also, as per convention, as per IUPAC convention, we will always look at the reduction potential of electrode, right. It's always the reduction potential that we would be looking at, right, unless it's specifically mentioned that it is oxidation potential. So whenever in numericals you will find the electrode potential, the electrode potential means its reduction potential, right. So we can write this oxidation potential of anode as minus reduction potential of anode, right, plus reduction potential of cathode, right. So reduction potential of cathode, we can denote it as, this is in reduction potential of anode left, right. We can write it as this plus this reduction potential of cathode, this, that is reduction potential of right, the cell which is in right, and the reduction potential and the oxidation and the reduction potential of minus reduction potential of half cell which is in left. So this is ER minus EL. So this is the formula for the EMF of the cell. So whenever you are asked to calculate the EMF of the cell, the reduction potential of cathode minus the reduction potential of anode, this is the formula for the EMF of the cell, right. I just repeat once more that the EMF is the maximum potential difference between the electrodes, right, when no current is getting drawn from, when no current is there flowing in the cell, right. And this potential, the potential difference exists because of the redox reaction that is happening in this cell. And redox reaction is reduction that is taking place in the right half cell, right, and due to this reduction reaction, this rod, this electrode has acquired positive charge. Similarly, due to oxidation reaction, this electrode, zinc, has acquired negative charge, and we know that positive is higher potential, is at higher potential, and negative is at lower potential. So there is potential difference, and current will flow from higher potential to lower potential. So current will flow from copper to zinc. right? This is your EMF, and EMF is measured using potentiometer. It's a device that is used to measure EMF, right? So this is important, right? This is important from numerical perspective. You get many numericals on this. So the difference of potentials between the electrodes of a cell, which causes the flow of current, right, from an electrode at higher potential, that is copper, to an electrode at lower potential, which is zinc, right, is known as electromotive force or EMF or cell potential, right? And EMF we know is maximum potential difference when no current is flowing, or when no current is drawn from the cell, right? And when current will start flowing in the cell, the potential difference will decrease, right? So EMF is always maximum, right? So I hope all this is clear to you, right? All this is very important, and we will be doing numericals on this, right, and various other problems, and you definitely get questions on these reduction potential and oxidation potential, mainly numericals. Thanks.